Welcome. I'm Wally Ritchie, WU1Y, and today we're going to run through the slides from the System Design Review workshop from July 30th. This workshop reviewed and discussed the baseline design for the P4XT Transponder project Phase 1 program. This workshop was an extension of a 4-hour face-to-face workshop that was held following Hamcation back in February in Orlando. You can get a recording of that workshop for the full 4 hours if you want, and that's available on the ORI website. So who are we? Well, Phase 4 Ground, or P4G, began in 2015. It was started by Michelle Thompson and others. The goal was to develop open source microwave ground equipment for the Phase 4B geosatellite. The space-based transponder for that project was to be a rideshare payload aboard a U.S. Air Force experimental satellite. The Air Force project was delayed and eventually canceled, but the Phase 4 ground work continued. P4 Ground started as an informal AMPSAT North America project. And in 2018, Open Research Institute was founded as a 501c3 nonprofit. The P4G project is now hosted by ORI along with Phase 4 Space and other open source projects. P4 Ground has produced a lot of useful code and FPGA pieces, all of which are open. P4XT is our transponder project. P4 Phase 4 refers to geosatellites. The X indicates that it applies to any future geosatellite, not a specific particular satellite like P4A or P4B. The project goal is to deliver a digital multiplex transponder that we call P4XDMT. It'll also produce a companion modem for use in low-cost earth stations. P4XT is now a formal ORI R&D project. The project is based on the idea that a major engineering project can be accomplished with volunteer engineers who are leveraged by funding for their tools, equipment, and hardware. The project funding levels are about $50K for the Phase 1 program, and that's already been committed. And the Phase 2, which is the full transponder, is expected to require about $500,000, and fundraising for that is already underway. These budgets fund only tools, equipment, and hardware, not engineering labor. The engineering labor efforts would require millions of dollars in traditional commercial or military settings. The volunteer engineering resources that will be used in the project come from the global amateur radio community, as well as the global open source satellite community and several other open source communities. So the project goals are two parts. The first is to produce a transponder design. This is an all-digital design to IF. The analog will be used only in the final conversions to and from microwave. The design is mostly software and FPGA code, and the FPGA source code will be Verilog or VHDL, together with the necessary timing specifications. These FPGA building blocks will be glued to standard platform building blocks like FIFO memories and multipliers. And all of this open source RTL will be fully verified and validated. The goal is to be able to have all of the pieces that would be needed to support a specific mission, and they'll all be demonstrated on suitable hardware. Specific projects will then only need to adapt to their specific mission requirements. A GeoComm system needs ground stations or earth stations. So the goal of the project is to serve the broad amateur community, and this requires that we have a low-cost, easy-to-install earth station. The heart of that station is a low-cost modem, and this is part of the P4XT project to develop this modem. This modem will have a high-performance DVB-S2 receiver for the downlink, as well as a GPS-derived station clock. And it will operate in a standalone mode without requiring a separate PC. Basically, the modem will use L-band IF inputs and outputs that will interface to LNBs and BUCs for the final RF stages at the dish. The cost target for the modem is to be well under $250. So why are we doing this? First, there's no ready-to-fly transponder payload. If we had an opportunity for a ride share, for example, this year, the community really has nothing that's ready to fly, nothing that's even close. Secondly, analog bent pipe transponders, the traditional transponders, have some shortcomings compared to digital. One is they have a relatively inefficient use of the bandwidth. They're subject to unauthorized hijacking, which is pretty easy to do. And they're subject to interference, especially when there's a lot of ground stations, and particularly when the ground stations are shall we say, unmanaged. So these are all things that we can overcome using an all-digital design. Another thing is that we really don't have any reliable amateur satellite disaster capability. It's basically non-existent. And that's disaster relief, emergency communications. Those are things that are ingrained in amateur radio, and it would be nice to have a reliable capability that can enhance MCOM. Paper designs, demos are all nice, but they're really not enough if you want to convince someone who has hundreds of millions of dollars of satellite at risk, potentially at risk. You have to have a proof that you can do what you say you're going to do, and that it's going to work, and not interfere with their investment. Radio arts today are now at least 95% digital. So the days of analog are really close to being gone. Which leads to the huge educational opportunities that we have by educating hams, particularly younger hams, in the digital side of radio. So what are we going to do with this transponder if we can successfully design it? Well, first we can use it as a hosted repeater payload on a ride share to geo like the 4B project. If an opportunity like that is presented, we want to be able to take advantage of it right away. Second, the DMT can be a repeater payload for a dedicated 6U or larger satellite that we actually put in space from the amateur community. P4 Space has a project in the early stages of looking at that, and there are other opportunities as well. Another potential space application involves the Eris Gateway missions, where there's a need for high-speed data and video, and there's a role for the DMT to provide comm services related to those missions. Related to that, we could have demonstration flights earlier in LEO involving the transponder and demonstrating capabilities that might eventually be moved to gateway. Finally, the transponder is a usable payload for a comm payload to support low Earth orbit missions, particularly those with 3U form factors, and those that require large amounts of data, where the DVB-2 is a good choice for space to ground. On the ground, we can use a DMT as a ground-based repeater as part of a QO100 hybrid setup that we'll talk about a little bit later. It could also be used for local digital repeaters in an application where there are line of sight to support microwave and large numbers of low-cost stations with capabilities for video and high data rates. It's possible also to use the DMT receive capabilities as part of an astronomical receiver, where the wide bandwidth is useful for analyzing pulsars and other radio astronomical objects. As well, that the dish, the 18-meter dish that the Deep Space Exploration Society has, can also be used for two-way comms to deep space or lunar. And then there's applications that nobody's thought of that could take advantage of the high data rate capabilities on aircraft, balloons, sounding rockets, etc., things like that. So the project is organized into three major phases. These phase numbers are kind of traditional military government phase definitions, where phase one is feasibility. And what we're trying to do in phase one is demonstrate functional hardware, RTL, and software, demonstrate a full DVB-S2 transmitter chain that's implemented in RTL and operational on the hardware, develop the remote tool chains that we need to support the development, not only during phase one, but as we move on to the development of the full transponder, and as well put in place a verification and validation framework so we can prove that the code works as designed and that the design meets the need. Finally, in phase one, we will need to have a complete definition of exactly what we're going to do in phase two and how we're going to do it. The phase two program is basically producing fully functional prototypes with everything and something close to the final hardware. So this means a fully functional DMT that has the multi-channel receivers, has the wideband and narrowband multiplexers, has the authentication, authorization, and allocation protocols operational, supports variable coding and modulation, one of the primary features of DVB-S2, where we change modulations on the fly, and the necessary framework to do over-the-air reconfiguration. In addition, in phase two, we'd have a fully functional ground-based repeater working through a QO100 that we'll talk about a little bit later. The next thing after phase two is actual production deployments to specific space missions. Those could involve Aris Gateway, a 6U GEO, or various spacecraft that different partners might have. Phase 2 will probably, or Phase 3 will overlap in many cases the Phase 2 program. Most people on this call are already familiar with geosynchronous orbit, but not everyone has a good feel for the differences between geo and low Earth orbit satellites. Usually, when you look at portrayals, they're not to scale, so they're highly distorted in terms of the relative shapes and distances. So on this slide, we have an actual to scale portrayal of a geosatellite along with the Earth viewed from from the North Pole. Down here at the bottom, we have a polar orbiting satellite at 850 kilometers above the surface, and you can see that the LEO space shuttle type orbits, ISS orbits, are even lower than that. They're basically riding the globe very close. When we get out to geosynchronous orbit, it's a long way away, relatively. When you look down at the Earth from geo, the Earth is in a field of view that's only 17 degrees, so maybe 30 times the width of the moon or thereabouts. There's other orbits. The GPS satellites are in orbits roughly halfway from between the Earth and geo. So when the transponder, the DMT, is deployed in a spacecraft, a dedicated spacecraft, our baseline package that we're thinking is 6U. This is an illustration of a 6U satellite. This particular one is a AAC Clyde Space Epic platform, and you can see that this type of satellite would have multiple solar panels and most likely radiators would be needed in addition to the panels. This view is a different 6U, same form factor, but it gives an idea of the relative size. Basically, the whole package is equivalent to a small PC, mini PC type form factor. This particular package here is a somewhat larger, 3 panels on each side. This configuration can supply 120 watts of peak power, which would enable a pretty decent downlink power level for a dedicated repeater. The various gizmos and electronics in a CubeSat usually follow a form factor that's roughly 90 millimeter square boards. These are some examples of off-the-shelf pieces that can be purchased. This slide shows a stack of 4 modules, 4 boards. This is roughly what we're talking about for the full DMT in a one-to-one redundant configuration. The canceled P4B project was planning to use a RINCON AstroSDR. That's a single board design that's shown here. This design has an off-the-shelf first generation Zinc 7045 FPGA and a analog devices 9361. The interface between the FPGA and the radio chip are parallel in this case. The device also has DRAM and radiation hardened power supplies, and you can get these off the shelf. So what do you do with the DMT as a repeater? Well, what we're trying to do is provide a 24/7 ham user experience through the satellite that's always available. And this would include random point-to-point push-to-talk comms, traditional CQ calls and QSOs, support as well one-to-many communications for RAG chewing, net operations like South CarsNet, National Traffic System message handling, MCOM, special event supports, the things that you can do on the current ham bands. This would all work in an appliance like operation, suitable for mass adoption, basically off the shelf. Install the dish, plug it in, and it works. That being said, in the ham spirit, you'd be able to do whatever you want to roll your own homebrew station using pieces or doing it all from scratch. Everything's open, everything's published. The modes that would be supported would include classic push-to-talk voice and digital keyboard RTTY styled conversation text back and forth. Both would be supported at the same time. We could also support, as we see the value of today with COVID, a Zoom-like conferencing capability where you have a presenter and participants that could all participate. This presentation you're listening to now could be done through that kind of a mode. Except it would also provide instant conferencing from any of the participants to participate. We'd have voice and text messaging modes, so you could record high quality voice messages and send them to someone as voice messages or text messages, arbitrary files, etc. Live video would also be supported over IP, and experimentation with the radio arts. So these would be all things that you could do through the satellite, and it would be available 24/7 to everyone in the coverage area. With our digital downlink, we have a lot of capacity, and we're not even thinking about analog for that. However, on the uplink, we can receive just about anything. So instead of decoding the digital modulations as we normally do and forward them through, we can also support forwarding the raw IQ data streams that are received. So any analog transmission would be simply converted to raw IQ and sent down the downlink. So this would allow what we call a virtual analog channel, and that would allow people to experiment with new modes of operation, be they digital modulations or analog modes or even standard single sideband. So this would support experimentation through the GEO uplink segment. The received IQ baseband will be forwarded over the DVB-S2 downlink. The samples, the IQ sampling could be 1x, 2x, 4x oversampled, and typically 16 to 24-bit analog to digital formats. The data stream would be pretty large to send the raw samples down. We're talking roughly on the order of a megabit per second, but we have that kind of capability in the downlink. We could also provide instrumentations, for example, power spectral density displays, spectrum analyzer type display. That requires relatively low bandwidth. The IQ data could be forwarded through in real time, or it's possible also to store it and forward it at a lower speed where it can then be played back later. And this could support standard channel spacing, 6 1/4 to 25K type channels. We would probably have adjacent channel guard bands so that interference would be lower than it might be in our packed normal digital channels. And to use one of these virtual analog channels, you'd still require to go through the protocols and make an appropriate channel reservation using the authentication protocols. The channel could either be fixed gain, just forwarded through, or we could utilize the resources in the receiver system to provide an automatic gain control. And this would also supply the various instrumentation that we normally would have on channels, their power levels, etc. These features for these virtual analog channels we would want to support from the beginning using even the lowest cost modem. Now, we mentioned earlier using QL100 ground-based repeater, a kind of hybrid mode, using the space segments that already exist over Europe and Africa through the QL100 satellite. And basically, this diagram illustrates how that would work. So the yellow here are narrowband channels. In the case of Q100, the uplinks are in 2.4 gigahertz band, and the downlinks are in the 10.5 gigahertz band. And normally, all the stations, there's two transponders: a narrowband transponder that's about 500 kilohertz wide, and a wideband transponder that's about 8 megahertz wide. And those transponders are using different polarizations to separate them. So they both have uplinks at 2.4 and downlink at 10.5 at different frequencies. So the normal mode stations are typically using either the either the narrow band or the upper wideband. Wideband is used mostly for experimentation with digital TV, and the narrow band is typically single sideband and other analog modes. Now, what were the QL100 is a bent pipe, so everything it receives on the 2.4 band, it basically relays and sends down on the 10.5 gig band. And what we're talking about doing for this demonstration, or could even be an operational capability, is to use that bent pipe to send the uplink signal back down where it would be received by a high performance larger dish station, and we would locate the DMT transponder at that station, and we would only need one of those. It could have a backup as well. And then all of the stations that send an uplink, a digital uplink, those uplinks would all be received by the DMT, just like they would be if the DMT was in space. The only difference is they'll have twice the propagation delay because of the extra path through the satellite, but and their signal to noise will be somewhat degraded from that. Then what we would do is what would normally be our downlink, wideband downlink, we would send that through the Q0100 wideband transponder so that it could be received by all of the stations on the ground. So, except for the extra delays, the double hop, the system would work pretty much the same as it does when the transponder is in the satellite. It would not have the security features because it's still a bent pipe transponder, so anybody can basically just send their signal through and receive it. That functionality would be on the ground, but it wouldn't do you much good because someone could still hijack the satellite as they can today. But at least it would provide the ability to demonstrate all of the capabilities that we'll have when we move the repeater to an actual spacecraft. So this is a mode that we're planning in phase 2 to be able to either do it as a demonstration research type project to test out the system and how it would work and verify performance. And we could, if the operators so choose, Q0100 could be left in place to provide an additional digital capability on Q0100. The advantages of this kind of setup is the stations only need the DVB-S2 receiver. That's part of the modem. It's a very low cost. They would no longer need existing HF transceivers and transverters. The transmitter would be very simple. It just would operate at 2.4 gigahertz instead of the 5 gigahertz that's planned for the North American satellites. And its power levels would only need to be 1 or 2 watts, relatively low power levels. It would be all digital voice. The only expensive equipment is that at the central station, which is basically a one-off. So each of the stations that utilize this would be very low cost, very easy to install. And all of this would coexist completely with the existing analog modes that are used on Q100, as well as the existing wideband modes for TV. So we might only occupy maybe 1 megahertz of the downlink bandwidth, or we might even, if the operators so choose, replace the standard 2 megahertz wide beacon with a signal that would carry all of the digital signals through the satellite as well. So there's a lot of different ways that this could be handled. So why are we using DVB-S2? Well, there's a number of reasons. First, these are standards that are international. They're free. They're widely used. Anybody can obtain all of the technical information on the standards without paying any ransom to anybody. The S2 version of digital video broadcasting is the second generation, so it incorporates a lot of things that were learned in the first generation of digital television broadcasting through satellites. DVB-S2 basically decided to replace some schemes that were used to pack data inside of MPEG streams that were used in the earlier generations, and instead have a generic stream encapsulation approach that's available, and that's the primary defined way for future downlink data. That's the things that are other than broadcast television. In DVB-S2, we have a quasi-error-free downlink. The error correction codes are very powerful. So basically, the channels are roughly equivalent to error-free. In television applications, you're talking about 1 frame a day. For DVB-S2 also has variable coding and modulation. This is probably one of the biggest features, where the modulation and coding can change on a frame-by-frame basis, which lets you share a single downlink carrier among stations with varying performance levels. So that's an important feature that we're taking advantage of. Now, in DVB-S2, we have a continuous transmission of frames at some symbol rate. So the symbol rate is fixed at some baud level, and all the frames use that same symbol rate. However, the modulation and coding can be changed on each frame. So a frame could be QPSK or 32 APSK, and that can change frame by frame. As well, the level of error correction code can change frame by frame, from anything from 910 to 1/4. The standard supports both linear and nonlinear modulations. So if you have saturated output stages, then QPSK and APSK modulations are normally all that can be used. If you have a linear or quasi-linear transponder, you can use more advanced modulations, 16 APSK and 32 APSK. And there's additional modulations, both up and down, available with the extensions, DVB-S2X. The error correcting codes are very powerful in DVB-S2. They use a combination of the low density parity codes and BCH codes to correct any residual errors left over from the low density parity code correction. The nonlinear modulations are QPSK and APSK, and these are constant envelope signals, the familiar constellations, and this is well-known digital arc going way back, and it is still a very efficient, high-performance way of transmitting when you're working with AWGN channels that don't fade like we have in satellite comms. In the linear modulations, we're varying not just the phase of the signal, but also the amplitude. So these result in waveforms that are no longer constant amplitudes, which is why a linear transmit chain is required in order to reproduce these signals. So the 16 APSK signal basically has a QPS-like signal at one amplitude, and changes the amplitude, and has other phases of the signal at a higher amplitude. And basically 32 extends that to 3 rings of signals. And these can also go out to 64 and 128 when you're using the X extended versions of the standard. The performance of DVB-S2 with its error correction is really good. It's very close to the limit, theoretical limit. In this diagram, we see the the dotted lines are the Shannon limit, and the solid lines here are the performance of DVB-S2, and this is over AWGN channels. And you can see that it's very close. It's within half a dB of the theoretical performance. Compared to DVB-S2 that used the convolutional coding, the performance is much better. But you can see that it's almost not worth improving much more from where the standard is. So that means this type of error correction encoding is something that's likely to last for a long time. The performance of the different modes in the standard is tabulated in a table. You can find this table in the standard documents. This is performance both in terms of the spectral efficiency and the ideal ESNO that's required to receive quasi-error-free signals at that level. The coding performance is so good that you can see on this chart where we have a packet error rate on the left ranging from 1 in 10 frames being in error at this line here, and on the other axis having the ESNO of the signal. You can see that moving only half a dB is enough to change the performance from basically an error every 10 frames to essentially error-free. And all of this happens within only half a dB. So basically this results in a system where it either works or it doesn't, based on what carrier to noise ratio you have at your station and what coding is being used. You can see that if you use the most robust error codes, your signals can be below the noise. If you're using higher performance codes, you still have very good error correction performance, but you require a signal level that's much higher. For example, in this case, 6.5 dB would give you essentially an error-free channel with an 8 of 9 coding. Drop it down to 6 dB, and basically you have nothing. It's basically no signal at all. If you were trying to receive 1/2 FEC, you wouldn't be able to do it. You'd have to have at least an ESNO of 6.5 to be able to decode the signal. So our downlink in P4XT and this is the baseline. We're planning for the carrier to be typically 10.455. We have 50 megahertz available in that band, and we would need to provide the channels to allow for the possibilities of multiple satellites in the future. We could also operate in the 24 gigahertz band, or even both. Basically, it's a single downlink carrier, so it's only one carrier in the system. It's not a shared. It's not shared at the analog level. There's a single signal, modulated signal that is in the downlink. We most likely, for our applications, use a saturated power amplifier because of DC efficiency reasons. We can operate when you have an inefficient amplifier stage. You have not only the problem of lower output power, but you have to get rid of the dissipated heat. So the closer you can run to a high efficiency, the better off you are. We're thinking in terms of 8 megasample per second or 8 megabaud sample rate in the system. And it would normally use QPSK or 8 PSK modulation to be constant envelope and compatible with saturated output stage. All of the stations, every station that listens must receive the downlink and would have that capability. Basically, receiving the downlink is a necessary part of everything. Whether it's receive only or transmit, basically all stations have to receive and track the downlink carrier. But it doesn't mean that they have to receive everything that's going by, because the modulation changes from frame to frame. Stations may or may not have the capability of decoding every frame that is sent. But they all have the ability to follow the synchronization and pick up with the next frame. So from a logical view, the DMT looks like this block diagram here. The yellow blocks are RF. This is on the receive side uplinks and the downlinks. These top channels here are the wideband channels. They're all in a single band. And the narrowband channels. And these are also contiguous. These could be overlapping, all part of the same band. And we'd also have most likely an auxiliary receiver that was able to receive command and control signals. The green blocks here are the analog digital conversions. So basically we have a wideband multi-channel receiver that's basically receiving these channels and demodulating them to bit streams. Same for the narrowband and the aux. On the right side, we have a major block, which would be the focus of our phase 1 effort, which is the DVB-S2 Transmitter. And that produces our single carrier DVB signal. And we would also have most likely a command and control, much narrower, low bit rate channel as well. The blue blocks here are the major bit banged elements inside the transponder. The GSE formatter basically formats wideband signals so they can be packed into frames for the transmitter. We'll have an IP packet multiplexer, so basically wideband channels could operate either in a bit stream mode or an IP mode. Most likely, most of them would use IP. And then we have a narrowband multiplexer element that's basically an isochronous multiplexer running at 25 frames a second. And this supports basically n times 800 bit per second channels from the narrowband, and there'd be hundreds of these channels. So this multiplexer packs all those narrowband bits and transmits a 25 frames a second that encapsulates all of that data as part of the DVB to downlink. And then there's a control element that basically manages the entire system and executes the protocols that are necessary for channel allocation and things like that. For interfaces to the host platform, we'd have a CAN bus, an RS422 bus, LVDS signals for differential low voltage signaling, as well as high-speed SerDes interfaces that we might use for video, things like that. When we move to the physical architecture, we would have most likely 4 boards. We would have, this shows a redundant configuration. We're planning on having one-to-one redundant capability from the beginning. So we would have both primary and secondary baseband processors, and these run completely in the digital domain, no analog signals whatsoever. And then we would have primary and secondary digital radio boards, and these would contain the radio chips, which contain not only the A to D conversions, but they also contain the some signal processing of their own to do frequency translations and filtering. We're planning on using digital radios that support JESD 204B interfaces. So these are high-speed serial interfaces to communicate between the boards. So these each of these blue lines indicates one or more pairs of lanes that go between the boards. And by utilizing these high-speed serials, these links are very similar to PCIe or SATA, USB 3, all modern high-speed links utilize the same basic technologies. And by using these, it gives us a lot of flexibility and redundancy. So the primary processor is able to talk through it would have lanes to both the primary board and the secondary board. And the same is true for the secondary processor. And both of them would talk to both CAN bus and our RS422 buses, not only to coordinate their own communications, but also for interface with the host system. So we're basically 4 boards to go from fully digital to analog at whatever. This could be either intermediate frequencies or final frequencies up to about 5 or 6 gigahertz. For 10 gigahertz, we'd have to have external conversions. And in most cases, the final RF stages would involve final conversions in the analog domain, as well as redundancy switching and antenna switching and things of that nature. Now the DVB-S2 transmitter block, that's our main phase 1 objective, is to have this completely operational. And what this block does is it basically transmits the baseband frames that we'll talk about in a bit. The transmitter pulls the frames from a FIFO block memory, and the isochronous frames that have to go out to maintain a specific frame per second rate from the narrowband multiplexer. Those frames would have the priority. If there are no frames at all available, then the transmitter would automatically send dummy frames. These are necessary in DVB-S2 because the transmissions are always continuous. The frames are sent back to back without any gaps. The symbol rate in the transmitter's fixed, but we can set it up so that at any given time we could be operating at a particular rate, and that could change over the life of the satellite. But in most cases, it would be stable for long periods of time. Each frame has its own mod code and size indication. So basically, a frame indicates what it will be sent with and what size it is. And the size is the size that is over the air in terms of error corrected bits. So the payload sizes are different for each different FEC coding. But the total package, including the FEC, has to be one of the standard sizes, either 16K or 64K. And we will most likely use 16K frames always, because we don't need that last bit of efficiency that's normally that you're trying to get normally when you're doing broadcast television. We'll always support QPSK and APSK and pilot insertion. We'll talk about that in a minute. And we'll support from the beginning the linear output chain. So the transponder will work either with saturated or linear amplifiers. And we'll support all of the forward error correction codes. The interesting thing about the transmitter is that it really doesn't care what the payload format is. It basically, whatever the bits are inside are transparent to the transmitter. It just sends the BB frame data, and that's basically it. Now, we already have a full working DVB-S2 transmitter, including DVB-S2X in GNU radio. This was done, a lot of the earlier work was done by Charles Brain, G4GUO, and Ron Economos has been done most of the latest work on this W6RZ. And basically, we have all of the blocks. So you can basically generate a signal if you have an appropriate SDR radio that is compatible with GNU radio, and this has all of the elements from packaging the BBB headers, scrambling, encoding with BCH coding, LPDC PC coding, bit interleaving and modulation, and the final filtering. So all of these blocks exist. These are software, so they don't work exactly the same way that they work in hardware. In addition to these blocks in GNU radio, we also have most of the RTL FPGA code to do the same things. Have also reached a working stage. So the phase one efforts will be focused on getting that RTL finished up and integrated and verified and validated. Now, the baseband frames or BB frames that we send are basically an arbitrary data field, and its format is described in a 10-byte 80-bit header, and the frames are padded to K bits, KBCH bits, and the padding is in order to make them come out to the right number that's appropriate for whatever forward error correction code is being used and what overall frame length is being used. So those bits that are in the BB frame have to be, the error correcting codes have to be encoded and added, and this includes the outer BCH code and an inner low density parity codes. So those are added to the frame to get one of the two standard sizes, 16K and 64K, for the entire frame. And these codes, these are systematic codes, so it means that the BB frame itself still has the bits, the raw bits as they are, and these are not altered in adding the coding to it. So the coding adds the error correction bits, and at the receiver, whatever errored bits are received in the BB frame get corrected using those codes. First, using the LDPC to correct everything, which includes errors that may be in the BCH coding itself. And then the BCH coding is used to correct and get to the final BB frame. So to send that frame over the air, basically it gets split or chunked into 90 symbol blocks. And every 16 of those blocks, the physical layer frame is going to have a pilot mark. That's in the case where pilots are used, which for us will be all cases. The frame itself is preceded by a physical layer header, and this contains a start of frame, 26-bit start of frame mark, and then a very highly coded code word that's easily corrected for multiple errors to get to a mod code, which describes the modulation and encoding for the frame. So every station to maintain synchronization, it expects to see the start of frame signal. If it doesn't have synchronization, that's what it will be looking for. And it expects to receive a code that describes the rest of the frame. Once it has this code, it doesn't necessarily have to have the ability to receive that particular coding. As long as it's in synchronization, it knows how many bits are coming. So it knows where to expect the next pilot mark, and it knows where to expect the next PL header. So this is what allows a DVB-S2 system to operate over a 20 dB different range of signal to noise ratios. Because the PL S-code header is very robust, all stations are always able to receive that header. So these are actually sent in half BPSK with heavy coding. So finally, there's a scrambler that runs that both sides are synchronized to, and this basically scrambles the energy so that it can be distributed over the bandwidth. The pilot blocks are not scrambled. The sequence is running continuously, but when the pilots are inserted, they are raw carrier signals. For modulations that are 8 PSK or more, inter-bit interleaving is used in addition to basically spread the bits across in time across the frame, and this allows the FEC coding to work a bit more efficiently in the presence of bursty type errors. Then after we're finished with the modulation, there's an output filter, and that has a roll-off. Different roll-off values are available for a particular system, so those can be specified. They do not change on a frame-by-frame basis, but you can specify a different roll-off. So back to the major functional blocks in the transponder. We have the generic stream format, encapsulation formatter, that's formatting the frames from the wideband receiver. The narrowband frames will have a priority that's higher than these. And for the GSE streams, it's basically a wideband, it's a stream for every wideband channel, if the channel chooses to use GSE. IP can also be used, so wideband channel instead can just transmit IP frames. Those IP frames are basically stuffed together using the GSE IP protocols, packaging standards, and those get sent as a separate separate stream. Then most of the channels will be handled by the narrowband multiplexer. This will handle hundreds of low bitrate channels, and these are isochronous, 25 frames per second. 25 frames is 40 milliseconds to match up with typical codecs, which use typically 20 millisecond frames. It'll be flexible and will support n times 800 bit per second channels. These can support compressed voice and data, and the data there'll be two alternate modes, so you can stuff data inside of silent intervals when there's no speech. In addition, for efficiency, the telemetry and log data can be stuffed in the channels that don't have anything to send. So that'll be something that the multiplexer will do. So this will take advantage of basically every bit that's available will be used for something. The channel acquisition protocols will run in the narrowband channel. So even if you're using a wideband channel that you're sending IP packets, you'll negotiate the characteristics of that channel and authenticate it using the channel acquisition protocols that run in the narrowband channels. So how will we do all that stuff? Well, when you have a 16 nanometer process, you can do an awful lot of things inside a 31 millimeter square chip. And what we're planning for the baseline is using a Zinc UltraScale Plus current generation multiprocessing system on chip. So this is the generation beyond what was in the AstroSDR. We have a range of sizes that we can use, from roughly comparable to what the 7045 had to maybe twice as large or half the size, depending on what's needed. The UltraScale, besides fitting more things, has a more robust architecture, especially for functional safety and redundancy and doing real-time processing. So that's it also has very extensive power management capabilities and power management islands, which we'll go over in a few minutes. So we have on these chips, they're basically FPGAs with attached processors. And the processors consist of several types. There's a fixed platform management unit that is basically a triple redundant ECC memory-based processor that handles the platform management, power management, system management, functional safety issues. and this operates in the lowest of power domains. There's another configuration and security unit that's another triple redundant processor that manages both secure boot processes and authentications, as well as cryptographic functions. So these two pieces are the configuration and security unit is not accessible. It's a Xilinx maintained unit for security, and the platform management unit is programmable. So our application will program this unit to meet what our requirements are. So in addition to these two units, we have two different processing systems. One is our application processing unit, which can be either 2 or 4 cores. And these are ARM A53 cores. And the ARM A53s have neon floating point instructions, memory management, embedded trace, etc. In addition to the application processing unit, there's another pair of processors called the real-time processing unit. And these are ARM Cortex R5 cores. These also have floating point, but they have more reliable memory. They have ECC protected cache, and they can also utilize the on-chip memories, which are also ECC protected. So with the combinations of the platform management unit processors, triple redundant, the RTU, which is redundant and can also operate in lockstep mode, meaning the processors run in a pair, and if the pairs don't agree, an interrupt is generated to reset the system. And then finally, we have an application processing unit running in the multi-cores. So these constitute the processing system. On some of the chips, there's also a graphics GPU, which we may or may not have use for. It can be powered down. So it's whether or not we use a chip that has the GPUs will be driven by other considerations, since we don't have any need for graphics. But we may be able to do some signal processing inside the GPU. Although with the amount of FPGA fabric that we have, that's probably unlikely. Then in addition to in the processing system, we have a lot of high-speed connectivity in these FPGAs, ranging from Gig Ethernet to USB 3 to SATA, high-speed transceivers, a lot of stuff, flash, SD cards, etc. Now, all of this is basically the processing system, and it can talk to programmable logic, and this is the FPGA, where we can do all kinds of things. And in addition to the normal FPGA fabric of gates and flip-flops and lookup tables, there are additional block storage and DSP slices, basically multiplexable multipliers, and other resources. There's some built-in pieces to the chip that aren't made. One of the things you can do in an FPGA is you can build your own stuff, your own hardware using the FPGA fabric. But in many cases, it's lower power to have those components already packaged in working modules that aren't using FPGA cells to do that, but are basically part of the chip built into the chip. So those things provide interfaces, and you can, for example, you can do PCIe either through FPGA resources or through built-in controllers. So it's a lot of stuff. So to recap, we've got on the single chip a processing system that has a platform management unit that's a triple redundant microblaze user programmable processor. We have a configuration security unit that's also a triple redundant microblaze, and that is not user accessible. It's fixed programming by Xilinx. Microblaze, by the way, is their internal processors designs that can be implemented in the RTL. We have a real-time processing unit that has a dual lockstep pair of Cortex R5s with vector floating point as well. These run in lockstep mode, so if there's a single event upset that causes an error, it will the processor will detect that and generate an interrupt so it can be handled. These can connect with the on-chip memory, which also has ECC. There's also some tightly coupled memory that's associated with these processors. Then we have an application processing unit that's a more traditional dual or quad core A53 with neon and floating point. That also has tightly coupled memory with ECC, as well as cache and vector floating point instructions. Then the chip itself has a 256 KB on-chip memory with ECC, and that can be connected to either system. And there's a built-in low-power DDR4 interface as well. That's normally we will use, because of the space application, we'll use the ECC memory. Some of the earlier chips, boards that we play with may not have ECC. And then most of the chips that we're looking at, in order to get the quad-core A53s, you get a configuration that also has the GPU. That's an ARM Mali core. We most likely will keep that powered down. Then on top of that, we have the FPGA programmable logic, which in this case, the mid-range that we're looking at has almost 500,000 logic cells, 500,000 flip-flops, 2,000 DSP slices, which are basically 16 by 27 multipliers, and 25 megabits of RAM. So it's a lot of stuff. The multipliers, these chips have twice what was in the earlier generations. You can never have too many multipliers for signal processing. The chip also has high-speed built-in connectivity for DisplayPort, which we won't be using except for test, maybe some test configurations. USB 3 running at 5 gigabit, SATA 3.1, PCIe 1 and 2, and transceivers, general purpose transceivers. In addition to that, the usual cast of peripherals: Gig Ethernet, USB 2, CAN bus, UART, SPI, Quad SPI for NOR flash, NAND flash, and SD support with a memory controller. So all these are built-in functions of the fabric. In addition to that, there's high-speed connectivity from the programmable logic, and that what we'll be using here is primarily the GTH transceivers, 16 gigabit per second, and those are what we will be using for the um, connectivity to the radio chips using JESD 204. So there are several chips in the family that can be used. We can use either the CG family or the EG family. Both of them have a reasonable range of sizes that will work in 900 pin packages or 1156 ball packages, which are the optimal sizes for what we're doing. A representative chip, or probably our baseline, if you will, is the ZU6. And the only difference between the EG and CG families are whether there are 2 or 4 cores for the A53s and whether or not there's a Mali processor for the GPU. We would probably take advantage of the 4 cores, especially because the power management is very flexible with these cores, so we can run what's necessary without a penalty. And as you can see, this column is the resources that are available in the 6 chip, and we can go up in terms of programmable logic and memory. We can actually go up to the 15 level using the EG chip. So we have almost capability for almost twice as much as what we're planning with for the baseline. And we can also move down and stay within the same chip footprint. Now, internal to the MP-SOCs, there's a lot of connectivity. Some of it is built in. For example, the DDR memory controllers are built in, including the ECC. And these have routing that allows them to be shared between different subsystems. The on-chip memory is also flexible and can be switched between the application processing unit cores and the real-time processing unit cores. So things can be configured basically however you want them. And in addition, there is connectivity to connect the processing system to the high-speed resources in the programmable logic. So all of this is covered in the thousands of pages of documentation for the UltraScale Plus MP-SOCs. We'll be using the subset, obviously. Now, one of the big motivators for using UltraScale is its very flexible power domains and power islands. And this let us operate the different pieces on the chip from very low power levels to low power levels all the way to full power. So it's not necessary to bring up the FPGA fabric, for example, if you're in a low power mode. The processors that we would use in the low power mode would be these, the RPU, the R5 cores, because they will run in the low power domain. And they can be configured with different sizes of memory blocks. So we can even have them powered in a low memory configuration to save power. Then basically, depending on what mode the satellite might be in, you would bring up additional pieces of the chip when you had the power available to handle that. So those types of management activities are all possible within the structure of the chip. And the idea is basically things that aren't being used can be powered down very flexibly to save power. For high-speed I/O connectivity between the programmable logic and the processing systems, there's also a flexible architecture. There's some built-in transceivers that are running out of the box whenever they're powered up. And those allow you to do Gig Ethernet and PCIe2, SATA, and DisplayPort. So those are handled pretty much off-the-shelf connectivity just by configuring them. As well, the USB controller that's associated with the USB 3C, USB 3 high-speed channels, since every USB 3 also has a USB 2 for managing it. These connectivity blocks can also be hooked in through the programmable logic fabric. And the programmable logic, so these transceivers can actually be shared for that and utilized through components that are implemented in the programmable logic. Very high-speed connectivity, such as 100 gigabit Ethernet and PCIe 3 interlocking, those can all be handled as well. So these transceivers are a fixed part of the chip. There's four lanes, and then there's additional high-speed and medium-speed channels as well, and these are available through the FPGA fabric. And we will be using the GTH transceivers that will run up to 16 gigabits per second, and those will be used, multiple lanes of those will be used to handle our communication between the baseband processor and the radios. And speaking of radios, we're planning for baseline to be using the 809371 chips. We might use one or two of them on the baseband board. And these are the generation after the more common 936X family that has parallel interfaces. And the reason for switching to this family of chips and newer ones that succeed this one is to take advantage of the JESD 204 connectivity. In addition to the flexibility and ease of the connectivity, it's also intrinsically more reliable, because we can, if we lose a lane, we can reconfigure and work around hardware issues that might affect a particular lane. It's difficult to do that when you have dozens of parallel interface bits that are going back and forth. Now the 9371 basically has two receive chains, and they have to share the same local oscillator. So you could use them independently if you're clever about your frequency choices. You basically have two channels that can be derived from the same local, and it's the same on the transmitter side. So again, it's one local oscillator for the transmitter and another for the receiver. And these have a number of digital functions in addition to their analog function, but basically they go from analog through digital processes of decimation and filtering and offset correction, etc., and basically come down to a IQ data stream that's then transported over the high-speed JESD 204. There's a processor, an ARM core that's running inside this chip, all with manufacturer programming, to manage the functionalities of the digital radio portion of the chip. Communication with the host system is through a SPI port. Transmitter, same thing, just in reverse. It's using their receive lanes and transmit lanes on the JESD 204, and they can be flexibly allocated. One of the nice features of the 9371 is they added really two additional receiver sections. One they call an observation receiver, and this allows you to basically process your transmitted signal in another signal chain that can be used for things like dynamic pre-distortion correction and things like that. So these are widely used in terrestrial applications. In addition, there's what they call a sniffer receiver setup, and that's very flexible in that you can have several different analog inputs to this, and it has a flexible local oscillator, so you can basically tune different bands if you wanted to, and digitize these bands as an additional receiver. So you could use this, for example, to its performance is roughly equivalent to the normal receive system. So you could use it to handle an additional band, or to handle monitoring, or to monitor other bands. A lot of different functionalities, and it also connects directly to the JESD 204B core. So basically, the radio does a lot and transports the data in very flexible serial interfaces that it's roughly equivalent to using SATA. So the whole setup here is like going from parallel disk drive interfaces to SATA, except we're doing this in the radio domain. So that's the main motivation for moving away from the 9360 family to the 9371s. And there's a successor to the 9371 that on basically the same size chip packages even more, basically doubles everything up. So you've got another stack of receivers and transmitters, and a even more flexible and higher speed JESD 204 interface block. So we will be seriously looking at this chip as well. Again, there's always a trade-off of power and functionality, and but in many cases, even though a chip may be more power when running with everything running, if it has better power management capabilities, you may be able to actually improve the performance when using a subset of the total resources. So for working with the 9371, it's a complicated chip. It has a lot of functions. It has some filterings, and it needs a lot of support for a particular configuration of frequencies and functions. Filters have to be designed, and Analog Devices supplies MATLAB tools to do that, to basically come up with the coefficients that are needed so they can be loaded. So they have a reference platform that basically is, if you want to talk to them about how the chip works, about issues or problems, you're going to have to be doing it in a context of how does it work on the reference. So that's one reason why it's important to have a reference platform that uses their reference hardware design, which is this board here, and uses a reference platform, which is their, this uses the Xilinx 7045 chip-based eval platforms. And the reason for that is that was current common at the time that this hardware came out. So this is what's needed to do that, and all the tools. Analog Devices supplies RTL code for both the Xilinx and Intel FPGA ecosystems that handle a lot of the interface functions between standard transceiver components and the JESD 204 style implementation that is used on chip. This is a view of the same board. This is the evaluation board that is used with that. There are two FMC connectors, mezzanine connectors on these eval cards. The high-speed one is required to use the interface with the 9371 development boards. And this is basically the chip for the 9371 family. And most of these are just configuration connectors. Basically, the total amount of real estate required is very small. And if you recall, we had a pair of transmit channels, a pair of receive channels, and two observation channels and three observation and three sniffers, as well as clocking. Now, those the form factor of the PCIe based cards, the standard have everything with them modules from Xilinx. Those are not good for what we're doing. We really want to be running a package that's closer to what our final system is going to be. So there's a German company called Trends that makes a nice family of modules and accessories that incorporate the core functions, which are the DDR memories and the chip and its power supplies and clocking, and then have a very general purpose interface for the serial I/O. What's mostly high-speed serial I/O. So these boards are roughly 76 millimeters by 52 millimeters, and the chip, I believe this is a 900 ball size, I think, or 31 millimeters, something on the order of that. And these boards do not have ECC memory, so an ECC design would have an additional chip. These are 16 bits each, so there's a 64-bit wide memory. And if you use the ECC, it goes to 80 bits. And then these, I think, are the normal reference design for UltraScale is a 12-layer board. I believe these are 8-layer boards. you can get away with 8 layers if you're not using everything. And these boards use high-speed mezzanine connectors to connect to another platform, which is used to support the development cycles with these boards. So it turns out these modules can be had for less than the cost of the chips. Just a quirk of the way FPGA pricing works. But you're talking thousands of dollars per module. So Trends also makes a mini ITX carrier board, which is a 17 centimeter by 17 centimeter package. And the boards, the 76 by 52 module boards basically connect to this carrier, which then brings the high-speed signals out to a mezzanine connector. And this would be compatible with the 9371 mezzanine connector. And as well brings signals from these boards out to various standard peripherals. As we mentioned before, there's a lot of connectivity that's more or less out of the box, just has to be configured. And that would provide connectivity for USB, USB 3, Gig Ethernet, etc. As well as in this area of the board, these are high-speed multi-lane connectors that can carry 4 pairs of multi-gigabit signals in a very small form factor. And these are made by Samtech, and these are what we're planning on using for the connections between boards in the final system. This, for size reference, this is a standard SATA connector. So these things occupy a very small amount of real estate, and they are a high-speed latching connector that comes with prefabricated cables of different sizes that perform an ideal way to transport high-speed baseband signals between the processor and the radio system. This is a little better view of those connectors here compared to a standard 10-pin connector or a SATA connector. And these are in a pair. They actually have a pair for power, because there's a whole family of these connectors that deal with optical connections that need power, as well as copper connections that we'll be using. Then a 9371 card can connect here initially for evaluation, and moving from the reference platform that we'd use to talk to ADI if we had to, and establish a common platform to talk about, and then our specific platform with the specific FPGA chips that we'll be using in from a later family. We can still retain those development boards for use here. This is the bottom side of that board. These, as I mentioned, are they're actually ITX connectors, and they will fit in a standard chassis that can hold 2 of these. Holding 2 allows us to easily configure the redundancy features during early testing and developing support for that. So a simple 2U rack mount case can carry 2 of those systems. So what we're going to need to produce the transponder, the full DMT, there will need to be a number of documents that fall out of the development process, and all of these will be occurring during the phase 1 program, and they include a system architecture reference that also has the roadmap, if you will, for the whole system, a downlink specification that describes in complete detail the downlink, a narrowband uplink specification that describes in detail the narrowband uplinks. Those are the ones with channel sizes that'll be something up of 25 kilohertz or below. And then a similar wideband uplink specification to deal with the wideband higher speed channels that could be anywhere from 100 kilohertz to a megahertz. There'll be a specification for the narrowband multiplexer. This is a fairly complicated and critical piece of the system because it's what basically allows us to package hundreds of channels very efficiently and pull out the bit streams for any channel that the user wants to deal with, or all simultaneously. So that's a critical specification, and it's mostly describing the formats for the stream, which are the bits packed into UDP packets that are carried on the isochronous frames. Then finally, we'll want to have a application to radio API that will allow decoupling user interface type programming from the radio core itself. That way we can leverage the best of open source world in terms of people coming up with improved ways of handling the user interface for different kinds of applications. So in order to do that cleanly, we want to have a clean API for how an application program talks to the radio stack, and for the baselines, most of what we'll be doing will be relying on HTML5 type applications. So to get all this work done, we're going to have to organize the various teams for working on the DMT. And as we see it now, the teams that we're going to need will include a build integration team, and that team will be responsible for handling the PMU programming, configuration of the overall system, booting, all the processes that it takes to basically make the platform work. We'll need another team that will work with the RPUs. These are the ARM R5 cores. They could run anywhere from bare metal to an R10 operating system. They will not be Linux, but they could be real RTOS or whatever to be determined. It's a little bit different than the standard operating system here, so R10 may be a good choice because it's designed for to be able to work with lockstep. But whatever that, the RPU team will put together those decisions and put together the RPU platform. which is basically what runs in the low power domain and manages the system um, prior to bringing up the power hungry stuff. Then we'll need an APU team that will be dealing with the A53s and what they run, which include the authentication, authorization, and channel access protocols, and the protocol controller that will talk to the devices for the purposes of authentication. That APU will also be doing a lot of setup activities, flipping various bits in the FPGA fabric to route channels from one place to another, for example. Then we'll have at least one, probably more, FPGA teams, and these will focus on specific packages implemented in the FPGA core, the programmable logic. And this will start with the DVB-S2 Transmitter. That's our key goal for phase one, is to have all of the framework plus this important transmitter module working. The FPGA will also have to, team will do the various blocks to build the various framers and the narrowband multiplexer. And in addition, there'll be two major projects, one to handle the wideband multi-channel receiver for the wide channels. This could be something like 32 to 64 of these. And then handling the narrowband receiver, which will be many more channels. That could be as high as 1,000 channels, depending on the implementation. Then we'll need an RF teams to handle the final pieces. Everything above is basically produced our IQ basebands. And the RF team will have to deal with that downstream, beginning with the digital radio pieces, the 9371 or whatever chip we use on the as the radio chip, and its configuration, which involves quite a bit of work. And then the final analog chains for which will depend on what frequencies that we're going to operate on. We'll probably prototype chains for all microwave ham bands. We'll have a team that will handle the PCBA, the circuit board layouts. The one that's most critical, of course, is the one with the FPGA, because that'll be 8 to 12 layer board. So we have that layout to do, and then there'll be other layouts for handling the digital radio boards and handling the various RF boards. So there could be several different teams, project oriented. And then finally, we'll need a project management for all of these activities. So that pretty much wraps it up. This is I hope gives an overview of where we're at. Where the plan is to proceed to write up more of this and have enough documented so we can have a semi-formal actual design review where we make whatever decisions we need to make for carrying out phase one, understanding that by the time we reach phase two, things will change, and phase two will probably look a little bit different than what we think from here, but most likely along the same lines. There's more information available on the mailing list, the Git repos, There's collaboration that occurs every single day in the various Slack channels that we have. We'll be expanding those as this gets underway. And the website has policies and descriptions of other projects and a whole bunch of other stuff. So you can follow the link for open research and find all of the information there. And you can feel free to ask any questions on either the email list or the Slack channels, either about the things that we've gone over in this presentation or anything else that comes to mind. So thank everybody for participating, and we'll see you on Slack.